back to my YouTube channel. We'll be dealing with engineering physics, right? We have given this typical question 1.2 says 1.5 kilogram of a gas at a temperature of 320 Kelvin and pressure of 126.25 Kelvin Pascal is compressed identically to a pressure. This is T2. Its pressure is P2. That remember 2. That means 2. This is the pressure 2 of 958 kilopascal. Use the following value. We have given the CP specific capacity of 861 joules per kg and specific capacity of compressed volume there 615 joules per kg. Decreases. Calculate the work done during the compression when the work done. All right, so you know this part of the game ball, guys. How can we go about to reach all that? Because here, remember the work done, we have to have so far, remember the work done is given by pressure 1 multiplied by volume 1 minus pressure 2 multiplied by volume 2 divided by 1,37 right, minus 1. So my question is this: we have to calculate the volumes, then we are good to go, right? So let us calculate the volumes. By the way, if you have not subscribed to my YouTube channel or it is your first time watching my video, may you kindly subscribe, become the part of the family by subscribing to my YouTube channel so that you'll be notified whenever I post a new video. Become the part of the family by subscribing. All right, so nevertheless, let us indulge in this video. All right, so I will start by calculating gamma. We know, guys, gamma is Cp divided by Cv. Cv there, this is typically given there. We've given Cp there, we've given it. All right, isn't it? So it is 861 divided by 615. This will be what? If you punch that on your calculator, 861 divided by 615. All right, this is what it just gave me 1.4. all right, this is 1.4. all right, okay, I got that to be 1.4. all right, so we have that value, gamma value. Now we go to we know that R, guys, we've given is equal to Cp minus Cv now. So Cp is 861 minus 615. This will be equals to what? 61 minus 615. This will be 246. This will give you 246. Remember, this will be in joules per kilogram per degree Celsius, as we have been given there. So all right, we have now that. Why did we calculate that? Calculated this because we typically know that P1 V1 is equal to MRT1. We have this, we know we want V1, we don't have the V1, volume 1. This will be MRT1 divided by what? By P1. So let's try. What is M? The mass. Are we given the mass there? the mass they say there, it's 1.5 gram. 1.5. 1.5 is like 1 plus a half. Half is 1/2. If you add these guys simply as 1,5 like that, it's a 1.5. That is the mass. That means it's 1,5. R, we've just calculated it right now, which is 246. This is 246 there. 246. T1, temperature 1. Here we've given there in kelvins. We've given there in kelvins 302 kelvins. We have multiplied by 302 Kelvin. Divide this by pressure 1. First pressure before compression is this. Before the compression takes place, this is our pressure. It's in kilopascal, isn't it? 126.25. 126.25. All right, if I'm not mistaken, there kilopascal is the same as times 10 to the power of 3, isn't it? So right, this is what we have. We punch this on our calculator. We have 1.5 multiplied by 246 multiplied by 302 divided by what is this? 126,25 times 10 to the power of +3. This will simply equals to V1 will be equals to 0,883, right? It's in cubic meter. It's in meters per cubic meters. Obviously, it's a volume is measured in cubic meters. We have that. All right. So there's this formula. Since we have that, we have this formula: P1 multiplied by V1 will be equals to 1 y like that, gamma. P2 multiplied by V2 will multiply this by 1 gamma like that. So we have the pressure 1 then, which is the pressure. The first pressure, it was 126,25 times 10 to the power of 3. V1, we just got it, 0,883 multiplied by 1. The gamma, we just calculated it by ourselves. It was what is this? 1,371. This will be equals to P2. Let's check the pressure 2 there. We have our pressure is compressed to 900 and, as we can see, 958 kilopascal. All right, that is in kilopascal. Since you've used this in pascals, so also this you're supposed to convert that 958 kilopascal. 958 must be times 10 to the power of 3 kilopascal multiplied by V2, we don't know, multiplied by 1 gamma of 1,371 raised to the power of that, right? So the aim is to find here, the aim is to calculate. Let's find V1. By the way, if you find V1, if you do your maths, if you want V2, the aim is to find V2. If you want V2 there, you'll divide this, you'll take the square root, you'll take the root not of 137 1 like that. And then we'll divide, will be over this 126 comma 25 times 10 to the power of what of 3 multiplied by 0,883 multiplied by 1 raised to the power of what 1,371. Divide this by this, which is 958 times 10 to the power of 3. Then V2 will be equals to what? We'll try to punch all of these. I'll try, let me see. When I punch that, this shift factor, then there 1.371, fraction of the root 126,25 times 10 to the power of what? Of 3 multiplied by 0,883 multiplied by 1 times 10 times 1,371 all over this 958 times 10 to the power of what? Positive 3. This will typically just give me some this is 0,208. okay, this is what cubic meters V2. Now we can calculate our work done. We know that work done is simply equals to P1 multiplied by V1 minus P2 multiplied by V2. Divide this into 1,371 minus 1. Why did this? Actually, this is supposed to be what? Gamma minus 1, but we have gamma. Alright, so this is supposed to become what? Gamma, isn't it? So I just substituted that gamma. So pressure 1, we have there, it's 1 2 6 5 1 2 6 comma 2 5 times 10 to the power of 3 multiplied by V1, okay, equal we got that V1 simply 0,883 minus P2, which is 958 times 10 to the power of 3 multiplied by P2. V2 is that the one that we just got there, which is 0,208. all right, over our gamma there 1.371 1 comma, let's just use 1,4 because I think I got 1,4 here. I just round it off to 1,4. okay, let's continue with this one, but here I got 1,4, but nevertheless let's just continue to what we've used. here on the top, which is 1.371. 1.371 minus 1. This will simply give us what we want. The work that will be our work done. All right, so this work done, let's check, supposed to be 126.25 times 10 to the power of positive 3, multiplied by 0.883. all right, minus 958 times 10 to the power of 3 times 0.205. Divide this 1.371 minus 1. Sure, we're supposed to get some negative value if I'm not mistaken. We have negative 228.871. This must be kilojoules. All right, this is in kilojoules. Are we together there? That must be in kilojoules. All right, this is what we have in this typical video. All right, so we have this typical again video here. One typical question here. We have question 1.3 says the horn of a moving train is sounded at a frequency of 1250 hertz. The speed of sound in air, we should take that speed of sound in air to be 340 meters per second. All right, says calculate the following. 1.3 the frequency heard by a person, which is the observer, standing at a train station while the train approaches him at that speed. That is the velocity of this train. Note it's in kilometers per hour, must be in meters per second. So remember that the speed must be meters per second. Supposed to multiply by 1000 and divide this by 60. By 60 times 60 there. 3600 seconds, isn't it? All right. Says calculate the frequency of the heard by the person, which is will be just an absorb. That is what we wanted there. 3.3.1, 1.3.1. So we know that our formula there of this is simply just a Doppler effect of the source absorber plus that. Here it's our formula. We know, write the formula, the source like that. All right, so we have this. They want the frequency of the heard by the person of the absorber. Since it's approaching the, remember the absorber, it is stationary there. The absorber, it is stationary. The train is approaching. The train is approaching there. Hence, as is approaching, the frequency length will reduce. As it comes towards the, will reduce in size the frequency length. What I'm trying to say is, this train comes this direction, the frequency length will be reduced. That means the absorber will hear more of the frequency, because as the train approaches towards this person will hear higher frequency, right? Will hear the higher frequency then. So the frequency of the absorber, okay, of this source there, we substitute of the source What is the frequency of the source? The horn is moving at the sounded frequency 1250. We have there of the source, it's 1250. The one of the absorber, the velocity, remember, of the air, sorry man, the velocity of the air, they said we should take this to be 340 plus that of the absorber. Remember, it is stationary. If it's stationary, this must be what, 0 meters per second. So the will be plus what, plus 0. The velocity of the absorber, remember that guy is standing at the station, that means it's stationary, it does not move. Then divide by the velocity of the air is 350, then plus the velocity of what, of the source, which is the train. The source is train, but they said they've given us that to be 60 kilometers, so 60, but we supposed to be in meters per second, guys. Our velocity there must be in meters per seconds, isn't it? That is the speed of the what is this of the source. So we know that this is kilometer. We'll convert that, we'll multiply by 1000 to become in meter, then we divide in 1 hour, we convert to minutes, we multiply by 60, 2 seconds, you divide, we multiply by double, you double up the 60s, now will be in seconds. So this is the same as what, 60 times 1000 divided by 60 multiplied by 60, one like that. Remember, what is that? Is 60. Yeah, it goes like to convert that. All right, to convert, trying to convert, or you can put this once at a time. 60 multiplied by 1000, remember 1000 same as kilometer, divide by 1 multiply by 60. It's 1 hour. Again, to become in seconds, we multiply by 60 again. So this is what we have. I will punch all of this on my calculator. What will the frequency of the absorber? The frequency of the absorber, 1 2 like that into 340. All right, 340 plus now. Let me just do like this again. 60 times 1000 divided by 60 times 60. All right. What I will have there, this will be 1191, comma 5 will be 589. All right, that is what it's in hertz, must become that, the frequency of that, isn't it? Hertz. All right, we have that hertz. Then what do we want now? Given 3.2 says the frequency heard by the person when the train is just passing him. The frequency heard by the person when the train is just passing him, that means now it is going. All right, let's check now. It's just passing him, if it's just, guys, just, here is the person there, the train here is just passing him, is exact, it's at exact, remember this guy is not moving, it's at the 0 meters per second, it's just passing him. The velocity will be the same there, the same spot there, will be exact, that will be have equal velocity, it's exact, it's at the same straight line there, they will be at the exit point. We expect all of those velocity to become zeros. So for us to find that frequent, we're using our formula again of the air plus of the absolver velocity of that. So that means the velocity of the absolver visits of the source will be equal to the velocity of what? Of the, remember, just before it's passing, they will have the same velocity there, whereby this velocity is the same. All of them can just say 0. Then here we want the frequency there of the source you've given there, which is 1205 and 50, 1250. Of the air is 340 plus of the source will be 0. Stationary of the air is 340 is the same as that, will be 0. Then what else? This will have there the frequency have 125 into 340 plus 0. Now 340 minus 0, but still there's nothing there. Remember, here you're supposed to put minus because it's going away now from the source just before it's met, but still this does not affect anything. This will be 250. We'll have that heads, our heads there. All right, so this is what we have for that. Now let's go to this. Says 1.4 there. Says now an organ pipe has a fundamental frequency of 268 Hz. Neglect and correction. The velocity of sound in air we've given is changing there, is 334 meters per second. Say determine the length when it's open. Oh guys, when it's open, the fundamental frequency when it's open, guys, remember dealing with organ pipe. Do not forget, when it's open, guys, our wavelength will be equals to what, guys? Our wavelength there. Okay, let me just say, remember we have to multiply that by 2. We have to double up. We have to double up. Our wavelength must be equals to 2 times what? The length. We double up. But when it's close, guys, we 4 pull up again. Multiply that by 2. Remember, we have to multiply the length by 2. Will be 4. That, remember, when it's closed, you multiply again by 2, you'll have 4 like that. So if we can attack that typical question there, 1.4, if we can attend that typical question there, we have given that has 268, said 4.1 when it's open. We know that the velocity is equal to the frequency multiplied by the wavelength lambda. Then this velocity there we have given of the m is 334. The frequency is 268, but now I've said when we are doubling the length, this will be 2 times the length. If it's open, this will be 2 times what? The length. All right, then we want the length. If we want the length, we will divide 334 divide by 268 multiply by 2. So this will be equals to what? Therefore the length will be equals to what? To 0.633 meter. So again, we have now when it is closed, when it is closed, we still have the same formula. but this will simply equals to 4 L, because 2 multiplied by that will becomes 4, so we use that. We'll have a velocity again, still have this frequency 4 multiplied by L. Our L will be 3, divide this by 2, 6, 8 times 4, that land till 0,331 meter. So this is what we have. So guys, thank you for watching. Kindly subscribe, not forget to subscribe and click the notification button so that you'll be notified whenever I post a new video. Thank you for watching. Stay tuned, do not forget to subscribe, guys. Okay, feel free to comment and share this to your fellow classmates. All the best. See you on the next coming session.